Hello, everybody. Okay, let's start the third lecture of short course in stochastic introduction to nonlinear filtering theory and particle filtering theory. So, at the end of the last lecture, we were discussing about one of the main lemma that we are going to use to derive the Zakai equation, which is called, actually the number is as lemma 3.1, right? So let me quickly write down the lemma, and actually we proved the first two parts of this lemma, and actually it is remaining to prove the last part of this lemma, right? So what is the lemma says? So we have two simple processes, okay? Sorry, two predictable processes, defined on the probability space. Yes. Then with the hypothesis satisfying finite and expectation of 0 to, I'm sorry, see, this is 0 to t, and this integral also 0 to t of xi bar square dt is also finite. Then we have this following three results, right? Conditional expectation of xi s ds given gt is nothing but the integral 0 to t conditional expectation of xi s given gs ds, right? And conditional expectation of 0 to t of xi s bar ds given, sorry, stochastic integral with respect to the Wiener noise ys, because under the new probability measure, our observation process is a one-dimensional Wiener noise. Given gt is expressed as xi s, conditional expectation of xi s given gs. We have already proved these two results. So it is remaining to discuss the proof of the last result, right? Conditional expectation of integral 0 to t xi bar s dps. This is a stochastic integral. I mean, with respect to the Wiener noise B appeared in the signal process given gt, this is 0, right? Almost surely, right? So we have to prove this. So now we are going to discuss the proof of this, okay? So let's discuss the proof of the last result. So as usual, since xi bar is a predictable process, so we take, right, psi bar as a simple process, and we denote and we define a new set AJ, which is actually a sigma field generated by this psi bar, this process psi bar up to xj, up to xj, right? Because this is a simple process, right? At the beginning, we take psi bar as a simple process. Then you remember that we define our psi bar is as in this form, right? Psi bar j j s with psi bar j is fixed j measurable oh, j runs to 1, 2, and so on and so forth, right? So that means here this new sigma field AJ we actually generated from our process psi bar S up to the point xj, right? Now, so we want to argue that the increment byj minus bxj, right, is dependent the sigma field GT union HG. So we want to argue that this increment of the Wiener noise B over the interval xj yj is actually independent of the GT union HA. So this argument is very crucial to establish this conditional expectation vanishes, right? So how do we argue this statement, right? So we can see that this increment is independent of GT union AJ, since our sigma field GT is independent of the noise BT, right? And psi bar xj is fxj measurable, right? Fxj measurable. These are the two reasons that our increment byj minus bxj is independent of this combination of these two sigma fields, right? First one is our noise bt, that Wiener noise is independent of gt. Why it is independent? Because gt is nothing but the information associated with the observation process, that is the process y, right? Under the new probability space with probability measure p tilde, we have proved that yt and bt are independent. Okay, so that is okay. On the other hand, this psi bar xj is fxj measurable. That is how we take, right? Fxj measurable. And you can see that aj actually we we actually generate from this process psi bar s up to xj. That means aj, right, is a subset of fxj, right? And we know, on the other hand, we know that ft is nothing but the sigma field generated by the noise w s bs, right, to t. Because of this reason, this increment is independent of aj as well. So that is what we need. All right. So now we can carry on the proof. Okay. So therefore, so now you consider this conditional expectation, right, from 0 to t of psi bar s pps given gt, right? So this is equal to, since this is a simple process, as usual, this reduced to this form. We run from 1 to n. Conditional expectation of psi bar j, eyj, given gt, right? Now, now I am going to apply law of iterated expectation, right? That means tower property. Using tower property, you can represent this term as j run from 1 to n, conditional expectation of psi bar j b j b xj given gt union aj, right, given gt. So we used tower property, right? Okay. So I condition inside this conditional expectation, I again condition with respect to then this bigger sigma field. Okay, nothing changed. Now you can, why we did that? The trick is, once you do this, you can pull this term out. Sorry, not this term, I'm sorry. We can pull Kasai bar j out of this conditional expectation, because Kasai bar j, right, actually measurable with respect to this guy, right? Measurable with respect to this guy, because Kasai bar j is measurable with respect to aj, therefore Kasai bar j is measurable with respect to this sigma field. So now you can pull out, right, initial expectation of Kasai bar j of conditional expectation of byj minus bxj, right, given gt union aj, given gt. Good. All right, so now what we can do, due to this argument, this increment, right, is independent of this sigma field, right? Independent of this sigma field. Therefore, this conditional expectation is nothing but expectation of this increment, right? So this is j expectation of byj minus bxj given gt. So what is this? So the increment of the Wiener noise, standard Wiener. So this is 0, right? Therefore, this is 0, almost surely. So as usual, so we can carry out the similar procedure as we did for last proof of last 2 results, for the case where non-negative predictable process as well as the general predictable process, right? So then finally we can conclude the proof of this lemma. All right. Okay, that is the completion of the proof of lemma 3.1. Now we can derive the Zakai equation. Okay, so we have all the ingredients. We have all the ingredients to derive the Zakai equation. So theorem 3.2. Zakai equation. Okay. Zakai equation. So the unnormalized filter theta t satisfies the following stochastic differential equation. Stochastic differential equation, that is conditional expectation of f with respect to new probability measure p tilde, that is this duality pairing, equal to 0 f plus integral 0 t, duality pairing with unnormalized filter theta s with LF. This is the infinitesimal generator. Yes. Plus 0 to t theta s partial f beta plus f times h dys. This is the measure valued stochastic differential equation which solves the unnormalized filter theta t, where LF is the infinitesimal generator, infinitesimal generator of our underlying signal process, right? It is 1/2 a times second partial derivative of f plus alpha times partial derivative of f with is this function a is nothing but square of function beta plus square of function gamma. Beta is the coefficient of the Wiener noise W, gamma is the coefficient function of the Wiener noise B, right? And L is called the generator of the signal. So let's prove. So apply Ito formula. To our signal process under new probability space with the new probability measure p tilde. So that is dxt equal alpha minus beta times h xt dt plus beta xt dyt plus gamma xt dpt. So this is actually, we actually represent this as equation number 3.1, right? So we are going to apply Ito formula of for f of xt associate with this signal process, right? Then you get simply this representation d of xt. Well, because this is just a diffusion process, right? We have only combination of Wiener noises as a perturbation. So d of f of xt is partial f over partial f partial x xt plus 1/2 second partial derivative the quadratic variation of signal process, right? So let me write down the result once you apply the Ito formula. So you would get alpha minus beta h of xt partial f of xt dt plus 1/2 of beta squared xt plus gamma squared xt times second partial derivative of f dt plus partial derivative of f of t beta xt yt plus partial f of xt gamma of xt dpt. So this is the application of Ito formula, right? For f of xt, right? Now you can notice that this term associate actually with alpha alpha xt times this term, right? This term, and the term, the second term, this term, right, gives us the generator, right? Generator of the f of xt, right? So therefore, this reduced to d of df of xt equal, right, generator of L of xt, f of xt minus partial f xt h of xt dt plus beta xt dt plus gamma xt partial f xt partial x dbt. Right? We basically just combined this term together with alpha times this to obtain this one, right? Okay. Then you can further notice that the Radon-Nikodym derivative m tilde, right, which satisfy this differential equation. The m tilde t is h of xt m tilde t d yt, right? Okay. So we have differential of f of xt and differential of our Radon-Nikodym derivative m tilde t. So now apply the product formula. Product formula to m tilde t f of xt, right? for non-negative t. So what would you get? What would you get? So you get differential of m tilde t f of xt is nothing but m tilde t df of xt, right? Plus f of xt m tilde t plus the mutual variation of m tilde and f of x, right? So this is the application of Ito product formula for the product of two processes m tilde and f of xt, right? Then basically you have to plug this guy and this guy to these two terms, and you have to calculate the mutual variation using these two processes, right? Then simply you would get this. Let me write down quickly. M tilde t generator of f of xt minus partial f theta t h of xt, right? T plus beta xt partial left t dy plus gamma xt partial left of xt dbt. This is the first term. Gives us the second term is nothing but f of xt times m tilde t h of xt dyt plus the mutual variation of the process f of xt and m tilde t. So basically that is nothing but beta xt partial f of xt tilde t h of xt dt. Okay, so only the two terms, right? This term associate with process f of xt, and this one associate with the Radon-Nikodym derivative actually provides the mutual variation, this guy. So you can notice that this term cancel out with this guy. Okay. Therefore, finally, this reduced to m tilde t f of xt, right? Equal f of x0, right? Plus integral from 0 to t m tilde s times the generator of f ds plus integral 0 to t m tilde s partial f of x beta s plus f of xs h of x s times integrated with respect to noise y plus the last term 0 to t, right? Tilde s partial f of s gamma s dbs, right? So you can express in integral form, right? So once these two cancel out, these two terms cancel out, then you can integrate, right? From 0 to 0 to t, then you get this. Nice. What is the next step? Basically, you have to now take the conditional expectation with respect to new probability measure P tilde given the information actually provided by the sigma field GT. Both sides. That is what you have to do. So let's perform that action. Then you would get conditional expectation of, right, M tilde t f of xt gt equal conditional expectation of x naught, right, given gt plus conditional expectation of 0 integral 0 t, this guy, tilde sl x is given gt conditional expectation of, let's say, this is let's say this is term, let's say 2, 3, and this term, let's say 4. This is nothing but conditional expectation of term 3 given gt plus conditional expectation of term 4 given gt. Right? Basically apply conditional expectation with respect to new probability measure. So what is this? Left hand side. This is the integral, right? With respect to unnormalized filter, left hand side, right? That is nothing but f, right? And this guy is conditional expectation of f of x0 given gt. So that is theta 0, because m tilde 0 is 1, right? And these two terms, these three terms, actually you can further simplify using the lemma 3.1. That is what I mentioned, that lemma 3.1 is very crucial, right? You can see that here you have the conditional expectation, right, of this integral, right, stochastic integral. So you can basically bring this conditional expectation inside of the integral due to the first result in lemma 3.1. So therefore, that reduced to integral 0 to t conditional expectation of m tilde SL generator, infinitesimal generator of f x given gs ds, right? Plus integral 0 to t conditional expectation of m tilde is times partial derivative of f times beta plus function f of x, x times h of xs given sigma field gs d ys. Last but not least, when you take the conditional expectation of this term 4, see this term 4, this is a stochastic integral with respect to the Wiener noise B, right? And we take the conditional expectation of this stochastic integral with respect to new probability measure P tilde given the sigma field GT. Actually, we prove that that is 0, right? So that term vanishes, right? So we don't have that term appears. So now, so here you can see that inside this integral, you have the duality pairing of theta s generator of f s plus integral 0 t duality pairing theta s with partial f times function beta plus product of function f and h. Right. So that is the derivation of Zakai equation. Okay. So this is the derivation of Zakai equation. And you can notice that this is a linear evolution equation. All right. So basically, we use the lemma 3.1 to derive the Zakai equation mainly, right? Now, we can start the derivation of the Kushner-Stratnovich equation. In other words, FKK equation, right? That is the equation where the optimal filter pi t solves. So theta t is unnormalized filter, right? So theta t and pi t actually related each other with the Kallianpur-Striebel formula. So in order to derive the optimal filter pi t, so we first define the innovation process. The innovation process T by following a stochastic differential equation. d mu t equal dy t minus the conditional expectation of the function h of x t given original probability measure p, right? Times dt. So let's say this is equation number 3.2. So this is called innovation process. So what is the meaning of this innovation process. What is this dyt? This is observation, right? That is yt actually represent the observation process, right? Associated with the signal. This is the prediction, right? Prediction of the signal. So therefore, this is a kind of a difference between observation, measurement, and the prediction, right? The residual, right, of the observation and the prediction, right? The innovation is defined as difference between observation, measurement, and its prediction. Okay. All right. Good. Now, you will, shortly notice that this innovation process nu t is actually GT. Wiener process. GT Wiener process. Okay. So let's establish that fact. So nu t. Right? Let's establish this fact as a lemma. Lemma 3.3, the innovation process nu t is a GT Wiener process under the original probability measure under the original probability measure P. So this is a Wiener process. Okay. So let's try to prove this result. Right? Proof. Okay. So by stochastic differential equation 3.2, right? So you would have nu t is nothing but yt minus integral from 0 to t of this derivative pairing yeah. So first of all, our goal is to show that this innovation process is a GT martingale, right? It is a martingale with respect to sigma field GT. So in order to do that, so we consider for T bigger than S, we have, right, conditional expectation of mu T given GS. So you consider the conditional expectation of this new guy, the innovation, right, with respect to sigma field GS with respect to the original probability measure P. This is reduced to this expression. So just you can plug this one here, yt minus integral 0 t GS. All right. So now you can re-express inside of this conditional expectation. So inside this conditional expectation, you have yt minus this integral. So you rewrite it as follows: yt minus ys plus ys, right? And this integral from 0 to t, you actually divide into two pieces. One is from 0 to s, right? The second one is s to t. Yes. Good. Now, so what you can actually observe from the inside of this conditional expectation, this term ys is actually GS measurable, right? Because the sigma field GS is actually generated from the information that we obtain from the observation process Y up to time S. Therefore, this term is measurable with respect to GS. As well as this integral, right? This integral is also measurable with respect to GS, because this integral is associating with the information, right? So it is also measurable with respect to GS. Therefore, you can pull these two terms actually out. I mean, then this conditional expectation actually reduced to yt minus ys minus s to t dr given gs, right, plus ys minus integral 0 to s because this guy and this guy measurable with respect to GS, and using the fact that conditional expectation is a linear operator. So what is this term? This is nothing but mu s. Okay, then we have conditional expectation y t minus ys minus s to t r h r given yes plus yes. So now let's focus on the first term appears in the right hand side, this guy. So we are actually going to prove that innovation process nu is a GT martingale, right? So that is what we are heading to. So by using the fact that our observation process, right? Dyt is nothing but h of xt dt plus dwt. We have yt is 0 to t h of x r plus wt. Okay. So basically just plug yt and ys in terms of this, right, representation. Then you would get this term equals to conditional expectation of wt minus ws, right, minus integral from s to t, right, of h of xr minus duality pairing with the optimal filter pi and h dr given gs plus innovation process at time s. Once you plug, right, once you plug this expression instead of yt and ys here, actually you pick up these type of integrals, right? Then I actually absorb these integrals inside this, okay? That is how you come up with this, okay? This, right? Now, let's see what happened next. Okay. All right. So since conditional expectation is a linear operator, so you can express that first term appears in the right hand side as expectation of wt minus ws given gs, okay, plus conditional expectation of integral from s to t, right? Because we have here minus sign, okay? Then you have plus integral from s to t, duality pairing with pi r and h minus h of xr, right? dr gs plus innovation process nyways. What is this? So this is just an increment of the standard of the Wiener noise W, right? Given GS. So this is measurable with respect to GS, and this is therefore expectation of this increment, that is 0. Okay. Then you have conditional expectation of integral s to t. Let me express this duality pairing as a conditional expectation h of x r given gr, right, minus h of x r given gs dr plus mu s. Okay, so basically, yeah, so here you can notice that here, yeah, here I made a small mistake. Here, this integral is PR given GS still. Okay. Now, you can pull inside this conditional expectation of this integral s to t, because the conditioning actually holds at the lower endpoint of this integral s to t. Okay, therefore, this reduced to this expression integral from s to t, conditional expectation of h of x r given gr minus h of x r, right, given gs, right, dr, okay, plus nu s. Good. All right. Okay. Now you can see that you have a conditional expectation with respect to the sigma field Gx of these two terms. So then you can re-express that term as s to t, right? Conditional expectation of h of xr given gr, right, given gs, right, minus conditional expectation of h of xr given gs dr plus nu s. Good. Okay. So what you observe from the first term inside this integral, so we have iterated conditional expectations, right? So, and you can notice that so S is smaller than R. Therefore, GS, sigma field GS is a subset of GR. Therefore, this term reduced to conditional expectation of h of x r given GS, right? So you can immediately see that, therefore, this term cancel out with this guy. So what does it remain? Nu s, right? Yes, almost surely. So we started with the conditional expectation of nu t given gs, and we end up that is equal to mu s almost surely. Therefore, innovation process is GT martingale, okay, GT martingale, which is a GT martingale. All right. So which is a GT martingale. So GT martingale. Under the original probability measure, okay, under the original probability measure P, and also note that GT is the sigma field associated with the observation. So now we have proved that it's a GT martingale, but our goal is to verify that nu t is a standard GT Wiener process under original probability measure P. So it's just a couple of line proof to prove that it's a Wiener process. So now consider the quadratic variation of nu t is yt minus integral 0 t of duality pairing with respect to optimal filter phi and h. Yes, okay. So consider the quadratic variation, that is this is actually the quadratic variation only contributed by yt, right? So that is quadratic variation of yt. Quadratic variation of yt is t. Okay. So due to the Levy's theorem, nu t, right? Nu t is a GT Wiener process. So nu t is nothing but the difference of observation measurement and its prediction, right? So finally, it came up that which is a GT Wiener process, right? Under original probability measure. Now we can derive the Kushner-Stratnovich equation that solves optimal filter. Okay. So let me erase everything. So let me state the theorem. 3.4. Kushner-Stratnovich. We called FKK. Also equation. the optimal filter IT satisfies the following stochastic differential equation. For all f belongs to this class twice continuous and differentiable and also bounded functions. Okay. So basically we use the fact that this optimal filter pi t and the unnormalized filter, right, theta t are related by Kallianpur-Striebel formula. Okay, so we use that formula to derive the Kushner-Stratonovich equation. So apply, right, Ito formula to Kallianpur-Striebel formula. Belongs to C2 bounded R. Right. So we apply Ito formula. So let's apply Ito formula. Differential. So basically, you apply Ito product formula, right, for this. F equal of right. So this is nothing but 1 over duality pairing of theta t and constant 1, differential of duality pairing theta t f plus duality pairing theta t f and differential of 1 over duality pairing theta t and 1 and the mutual variation of these two guys. Okay, that is nothing but product of the differential of duality pairing theta t f times differential of 1 over theta t1. Right. So we just apply Ito product formula. Right. And also now we have to further investigate, right, this equation. So in order to do that, you know that the Radon-Nikodym derivative, right, m tilde t, right, which satisfy this differential equation, right? That is m tilde t 0 to t integral 0 t m tilde s h of xs ys, right? By taking the conditional expectation with respect to new probability measure p tilde given the information gt yes given gt, right? Then by applying lemma second result of the lemma 3.1, right? You can pull inside this conditional expectation. So this is 0 to t, conditional expectation of m tilde s h of xs given gs dys, right? Due to the second result of lemma 3.1, right? So what is this? This is nothing but the duality pairing of theta t 1. This is equal to integral 0 to t of the duality pairing of theta s h dys, right? That is the differential of theta t, duality pairing with theta t and constant 1 is nothing but the duality pairing with theta t and h d by t. Right? Actually, so this is the differential of this guy, right? This guy. Okay. On the other hand, you already have the Zakai equation, right? You have already derived the Zakai equation. Therefore, you have this is equal to yes beta plus f times h d by t. Okay. Basically, actually, by plugging constant 1 over here, you can immediately get this result again, right? Because generator is 0, this term vanishes once you plug constant 1 instead of f, you obtain this guy. And here it remains only, this is 1, then this is 0, then it remains this term, right? But yeah, this way also you can derive this equation, right? So we have both equations, right? In order to simplify right-hand side of this, right? Application of the Ito product formula for the Kallianpur-Striebel formula, right? Now, let's simplify further. Right? Since in the Ito product formula, you also have this differential of 1 over duality pairing with unnormalized filter theta t with 1. So again, you apply formula for this, then you get this as minus 1 over 1 square differential of 1 plus 1 over duality pairing with theta t and 1 to the power 3 times differential of 1 square. Okay. So we can further modify this result, differential of 1 over 1 equal to, so you can plug this differential 3.4 over here, right? This guy over here, then you would get minus pairing with theta t and h dy t over square of duality pairing with theta t and constant 1 squared plus the square of this differential, square of this guy. That is nothing but squared dt over theta t, duality pairing with theta t and constant 1 to the power 3, right? So now we have all the ingredients. You just need to plug this guy and this guy and this guy for the Ito product formula that we applied to Kallianpur-Striebel formula. Okay. All right, so then we can have differential of the duality pairing with the optimal filter pi t f equal yeah, let me quickly write down this 1 over t1 tf plus differential of 1 over t, duality pairing with theta t and 1 plus product of this differential, yeah, f here, f 1 over, just plug these expressions from this result to obtain the desired result. Okay, so this is nothing but 1 over duality pairing with unnormalized with theta t and constant 1 times differential of theta t, duality pairing with theta t and f. So this is actually the Zakai equation, right? So you plug that here. h by t. That is the first term. Okay, this term is okay. And the second term, right? So let me write down the second term. Okay. This term. So this is nothing but minus theta t duality pairing with theta f, conditional expectation. In other words, conditional expectation of f with respect to new probability measure times t h over of this guy by t plus this term times h squared over 1 cube t. Right? Then finally, I'm sorry. So this, I'm sorry, I made a small mistake. So this term corresponds to this guy, and yeah, right. This term corresponds to this guy. Now we are going to express this one, right? That is minus theta t partial f times beta plus f times h times theta t h over the duality pairing with theta t and 1 square dt. Okay, all right. So you can just, verify this one, just plugging into this formula, okay, simply and carefully you can verify this, all right. Now, you can further notice that in this first term, you can divide each term inside this bracket by this duality pairing, right? So then you would get, right? Plus partial f times beta plus f times h duality pairing over 1 dy t, okay, minus this term, right? So that is actually, you can gather, gather theta, the duality pairing with theta t and f, divide by duality pairing with theta t and 1, and also theta t and h with duality pairing theta t 1, 1. So, right, then you would end up with the t f 1 times theta t h over theta t 1, right, dy t Likewise, you can further execute same idea to obtain the following two expressions plus that is f over 1 times h over 31 square dt, right? Then we have last term let me write down it quickly, minus t partial f beta plus function f times h over 51 times h 31 dt. All right. Okay. So let me erase this guy also. So to analyze term by term, you can see. So what is this? By applying Kallianpur-Striebel formula, you can immediately see that this is the conditional expectation of the infinitesimal generator acting on f of xt given original probability measure p, right? Right. So that is nothing but pair in pi t L f dt. Likewise, here you have pairing with respect to pi t with partial f beta plus f times h dyt. And these two terms, these I mean minus these two, product of these two terms actually gives us pi t f times pi t h dyt. And last by not least, this guy gives us plus pi t f, right? This is pi t f times duality pairing with pi t and h square dt. Okay, we are in good shape, right? So now we have to further simplify right. So this is duality pairing pi t and left dt, and you can see that if you focus on this term and together with this term, duality pairing pi t and f and duality pairing pi t and h is common, right? So you can pull it out. So let me first write down this guy over here. beta h dyt. And plus, so you pull out, no, let's pull out minus the f times pi t h, right, times you get inside the bracket dyt minus t h t, right? So therefore this is equal to it, right, dt, right, plus, so what is this term? This is the innovation, right? Innovation process, right? Let me write down this first, pi t partial f beta plus h dyt plus minus pi t f pi t h d du t, okay? Okay, so we simplify further, and also here instead of dyt you can plug the right, in terms of the innovation process, because dyt is nothing but d nu t minus this guy, right? Then you can simplify further, then you get rid of this dyt, then finally you would end up, right, with the Kushner-Stratnovich equation, differential of pi t f lf t plus, okay, inside the bracket you have pi t partial f beta plus f times h minus f t h times d nu t, right? So it's just a simple manipulation, just plug dyt over here. In terms of the innovation process, then gather common terms like this and this, then you will end up with this FKK equation, right? So you can notice that this is a nonlinear measure valued evolution equation. See, you have this product of these two optimal filters, product of the two measures. So it's a nonlinear measure valued equation that which solves the optimal filter. But in Zakai equation, we don't have this term, this type of term, right? So that is why it is easy to handle the Zakai equation. So this is just the derivation of FKK equation, and also we derived the Zakai equation. So in this course, we are not going to discuss about the solvability of the measure valued Kushner-Stratnovich or FKK equation or Zakai equation. That means we are not going to discuss about the existence and uniqueness of a certain class of a solution for this. So it's another discussion, right? So you can define the solution that you are expected for according to the problem, and then accordingly you can prove that the solubility of the measure valued equation. So next chapter is the particle filtering method, because we know that it is most of the time it is hard to solve this measure valued equation analytically, so we have to use some numerical techniques to construct the solution. So in order to do that, we have to study about this particle filtering methods. So maybe tomorrow I will gonna start this section, last section, about this particle filtering approach, which is just a brief introduction about the particle filtering, and I try to discuss just one method in that lecture. Okay, thank you very much. So let's wrap up the third lecture. Thank you very much. Do you guys have any question or comment? Yeah, you have a question. Yeah, I can hear you.
Okay. I really appreciate your presentation yesterday about the proof of lemma 3.1.
I actually didn't hear you clearly.
My question is about the observation process.
Yeah.
YT.
Yeah.
In the proof of lemma 3.1, you
yeah.
use the fact that the observation process is a martingale. So my question, and when you prove that YT is a martingale, you first construct a probability measure and then apply the bias formula to prove that YT is a martingale. So my question is, why we cannot prove directly that YT is a martingale?
YT, so you mean lemma 3.1 or different proposition you are talking about? In lemma 3.1, we discuss actually these three conditional expectations, right? The first two conditional expectations, we can actually bring this inside the integral, right? And the last conditional expectation is 0. So probably you're asking about different proposition, I guess.
Right? No, Professor. In the proof of lemma 3.1, I think the second one, you use the fact that YT is a martingale. My question is
a proof of a second result, you mean?
I think yes, if I remember.
So martingale, yeah, just go ahead. So where do I use it as a martingale?
For the proof of the fact that YT is a martingale, you construct the probability measure and apply the bias formula.
Martingale under the new probability measure, right? It is not even martingale. It's a standard Wiener process, Brownian motion. That's why we proved that.
Yes, Professor. My question is why we construct the probability measure, why we cannot prove directly that YT is a martingale without construct a new probability measure and
Because under the new probability measure, it becomes the martingale, I mean, it's a standard Wiener process. Under the new probability measure, P tilde, or P tilde. Because under the probability measure P, it is not the martingale. So this is the observation, right?
Yes.
So under the original probability measure, probability space, this is not a martingale. We actually construct new probability measure P tilde such a way that this actually behave like a martingale. In particular, it is a Wiener process, right? Using this,
Okay.
Doolean dead exponential, right? We actually using this, right? Doolean dead exponential eta. T is nothing but how do we exponential of minus eta t minus 1/2 the quadratic variation of eta. Yeah, eta t you define as a stochastic integral.
Minus.
Here you don't have minus, sorry. Minus 0 to t h of x. Yeah,
S.
good. Yeah.
D divided S, yes.
Yeah, this is how we define, right? Then we know that due to the Novikov condition, this is a martingale, and further we analyze that. Finally, we prove that this is a standard Wiener process under new probability measure P tilde. Yeah, that is the fact we use in the proof of 3.1. Yeah, you are right.
Okay. Okay, thank you, Professor. Thank you. Thank you.
Okay, you're welcome. Any more questions? Okay, thank you.